Okay, so right now we're going to take a look at how to build our very own Connect 4 AI using GoLang. So the reason for choosing GoLang is that it allows us to parallelize the way in which we search through the search space. We haven't done that in this part. We'll take a look at it in the upcoming parts. And before we dive into how we've done this project, I think it's important to understand how Golang actually works and how we've made use of different concepts and how the code works in general. So before we do that, I think it's time to understand the layout of the board, and this is one of the most important steps in the whole process, which is defining the actual Connect 4 board. So Connect 4, the official version comes out as an 8 cross 8 board, so it's an 8 into 8 matrix, which is the representation we've chosen for us. So if you're gonna use that, you'll probably see something like this. It's indexed from 0 to 7, which is the standard way in which you index arrays. And again, uh, if you want to win in Connect 4, you have to connect um, 4 coins of the same color. They can be arranged either vertically, horizontally, or diagonally. So let's take the example in this case. So if you take a look at the figure on your left, um, we're able to see that we've got 4 coins arranged vertically on the column which has been indexed at number 3. Now, this is one other interesting point to note. Uh, like I've been saying, you can arrange these coins either vertically, horizontally, or diagonally. If you're going to arrange them vertically, it's fairly easy to search through uh, the matrix representation and to see if we've won the game. But we don't have to essentially rewrite the logic to check if there's a winner. We don't have to check horizontally again. We don't have to write separate code for that. What we can do instead is take the transpose of the board. So that's exactly what we've done. The matrix arrangement on the right is actually the transpose of of the Connect 4 board on the left. So what does that do for us? This basically means that if you're able to write the logic for either checking it vertically or horizontally, we can then extend it to the vice versa, just by taking the transpose of it, and that's exactly what we've done. And likewise, the same logic applies if we're going to do it diagonally. For example, if you've got an arrangement from the bottom left to the top right, as we're seeing here, then if we take the transpose of it, we'll get we'll be able to check for arrangements which cover top left to bottom right. So that's basically how we check through uh, to make sure to check if there's a winner. And again, like I've been saying, there are 8 columns. So after each move, the user has the opportunity to add a coin in one of the 8 columns. And this gets repeated throughout the game until there's a winner or we've got no other slots left in a particular column or the entire board gets full. So this is what we call the branching factor, which basically means for every state you have, it can have 8 successor states in the usual sense. And this is basically how we've represented it. So let's just say we have this state, which is the initial state. After that, I can add a coin in one of the 8 columns. So I can add it in the first column or the second column or the third column and all the way up to the eighth column. And if you take this arrangement, the one which in which we've added it in the first column, I can again add the coin of the other color in either the first or the second or the third, all the way up to the eighth, and likewise for all these states. And this just keeps going and going till we're able to find uh, a result. Okay, so that's how we've outlined the working of this code. And I think it's now time to take a look at the actual code itself. And before we take a look at the code, I want to show you guys 2 articles on Medium. So these articles actually served as an inspiration for this project. So the first one is by Laurie Hartika. In this he just basically builds a chess AI. It's a very interesting article, and I highly recommend that you guys read it. And the other article is this by Ansh Gaikwad. So again, this article also takes us through the steps of building a chess AI, and I've loosely based this project around the steps in which outlined by him. So let's take a look at the actual GoLang code. The code actually works out to about 450 lines. Let's take a look at it on a high level scale. So we're basically having a two-dimensional array of 8 cross 8 dimensions. This is the array which is going to hold the state, and this is how we're going to represent it and work with the Connect 4 situation. So the very first step is to initialize the board, and if you notice, I'm passing the variable which corresponds to the 8 cross 8 array by reference. So why am I doing this? This is because functions usually take in parameters by value. If you're going to do that, the changes, like for example, if I add a coin, it's not going to reflect subsequently, and we don't want that happening. So everywhere you see in this code, we'll be passing it by reference, so that the changes, they carry through. So let's take a look at how the init board function works. Okay, so as you can see, what we're basically doing here is initializing the 8 cross 8 matrix with all zeros. So that's the first step. You want to make sure they all have legal values. So the legal value in this case being zeros. Okay, so once that's done, it's time to actually go ahead and play the game. Now, before we play the game, we need to prompt the user and show them the current state of the board so that they can decide in which column they want to place the coin. So that's what the display board function does. This is again fairly simple. Let's just take a look at it again. So as you can see, it just prints the state of the board. Uh, and it prints it row-wise, and we get the output in the terminal. So once that's done, um, we then prompt the user to enter the column in which they want to drop the coin in. And as we saw earlier, the columns are indexed from 0 through 7, and depending on the column in which they add it, they'll be able to drop it. Now, in this part of the code corresponds to the situation in which the user plays against the AI. So the user corresponds to 1, and the AI drops in coins represented by 2. Now, after each coin has been dropped, we check if it's actually been solved. Before that, let's take a look at how the add coin function works. Yeah, so this is the function to add the coin in. Uh, okay, let's just take a look at how this function works. So if you want, before you do that, you want to make sure that there's actually space in that column to accommodate a new coin. That's what this part of the code does. And once that's done, you just add in the new coin. That's what this part of the code does. And uh, after each time we add in a coin, we just make sure that the board is in a valid state. So what does it mean that the board is in a valid state? So for example, if there are 3 red coins, there has to be either 2, 3, or 4 yellow coins, nothing more or nothing less. If it crosses that threshold, it means the board is inconsistent and we've made a mistake somewhere in our code. This is just, a sanity check, if you will, to make sure we're just heading in the right direction. Let's take a look at that function as well. So yeah, this is basically how that function works. We're just making sure that uh, the difference between the coins is less than 1 and not more than that. So that's how you add the coin, and then you make sure that everything you've done so far is actually valid and logically sound. Let's go back to the driver code. So once we've added the coin, now it's time to check if there's actually been a winner. The function to do that is called check solved. And like I've been explaining with the diagrams and illustrations, this is where we check if it's been solved horizontally, vertically, or diagonally. And again, we're taking in the board by reference everywhere. That's how the code is structured. Here we check if it's been solved row-wise. Here we check if it's been solved column-wise. And this is the logic to check if it's been solved diagonally. And here we take the transpose at 2 positions. This is to make sure we don't have to rewrite the code and that the logic which we've written for one thing can be extended to the other. So it's just safer and much more easier. And to make sure that this checking part actually works. We've tried out a bunch of different configurations, which I've just commented out here. But if you want to run it locally, you can just uncomment it out and then make sure it all works. We just after we add a significant portion of the code, it's good practice to make sure that everything you've added up until now works well on its own and works well together with the previous code you've written. So once we're checking it, we just go back and forth and add the coins, ask the user to add the coin, and then make the AI add the coin. Now we've been talking about the AI. Let's just take a look at the logic for that. If you take a look here, yeah, so if you take a look here, this is the function which corresponds to making the AI play the game. So the play game, let's take a look at the play game function. Okay, let's look at the function signature. The board basically represents the 8 cross 8 matrix, which represents the Connect 4 board at each instance. The turn denotes the coin, either the coins marked as number 1 or number 2. These correspond to yellow and red coins in the official Connect 4 logic. So this basically denotes whose turn it is to play, and D denotes the depth to which we're going to search. Now, before we do that, here we've made use of the connect of the MinMax algorithm. So the MinMax algorithm is basically a way to search the um, search space in a two-player situation. It's one of the fundamental concepts of AI. There are plenty of books and resources available online regarding this topic, and I highly recommend you guys that to check it out to understand how this works. I won't get into too much detail of that. So what we basically do is we like I said, the branching factor for this situation is 8 because there are 8 columns into which a user can drop his or her coin. So what we basically do is run through all of those 8 columns successively for a depth of 5, and we pick out the best move which maximizes our chances of success. And likewise, when it goes to the other user, our opponent is also going to try to maximize his chances of winning. So it's actually a zero-sum game where each person is going to want to try to maximize their chance of winning. But how will the computer know that this is a good state or this is a bad state? Well, that's where we score the board. And yeah, yeah. And in order to do that, we take the function which is denoted by current score. So this function basically tells us how good or how bad of a state we're dealing with. So as you will see, um, this function has been through a lot of tinkering. So one of the first things that we do is we try to maximize our own chances of winning, and at the same time, we try to reduce the opponent's chances of winning by blocking his moves. So that's basically what this code does. So we check for threats and we try to either counteract them or we try to win. And we've opted for a scheme where the scoring's a differential, if you will. So moves that favor us will be scored positively, as you are seeing here. If the situation in which there are uh, three coins already present in horizontal orientation, and a fourth coin can be added either in front or in the back, it's actually a very good situation, and we'll be able to win if that situation comes to us. So we're scoring it with a plus 10 if that turn corresponds to ours. Like, I mean, if the three coins are of our color, then it's favorable for us. However, if they're in the opponent's color, then he or she has a huge chance of winning, and we should do everything to avoid that state or to block that state. So in such a situation, we'll score it with minus 20. And likewise, if there are two coins aligned in such a way, and by placing a third coin, he's able to get a three coin orientation that can be harmful to us in the long run. And uh, after a lot of trial and error, I was able to troubleshoot this. So in such situations, we just give it a minus 5, and this basically goes on for all the possible orientations. So that's we saw the example for the horizontal orientation. This is for the vertical orientation, and this is for the diagonal orientations. So after each turn, we drop in a coin, which we assume to be the best uh, move for us, and then we let the AI play, and then we just move back and forth until there's a winner. Now let's take a look at how the AI actually plays. Okay, so since it's a GoLang code, you give go run and the name of the file, which in my case is main.go. Okay, so yeah, right now we're running the code. Let's play. So we'll display the configuration of the board, and since we're just starting out and it's our turn to start, everything has been initialized with 0. So I'm going to start off by, let's just say I want to drop it into the third column, and since it's indexed from 0 to 7, it's corresponding to 2. So once I do that, once I hit enter, the AI is basically searching through all the possible steps up to a depth of 5. So it's thinking 5 moves ahead, and then it's going to pick the move which it sees to be the best for itself. So now the AI has played and it's dropped its coin in the fourth column. So a column with index 3. So it's trying to, uh, capture this part here, or it can either go vertically. So these are the two moves which I think it's going to try and play right now. So I want to sort of block it. So I'm going to drop it in the fifth column. So I'm going to hit 4. And again, the AI is going to look forward and it's going to determine the best course of action for itself. Again, in part two, we're gonna take a look at how to implement alpha beta pruning. So alpha beta pruning actually helps us cut down the search uh, space, and we can also try to implement parallelization. So if you implement parallelization, you'll be able to speed up the code. Uh, that usually works for large games such as chess, where there are a huge number of moves after each state. I'm not really sure how it's going to work for our situation, but it's worth a try. So now the AI has dropped its coin over our coin. So it's dropped it on the third column, so which has been indexed with 2. So I want to, sort of try and capture this vertically. So let's just drop it in the fourth column again and see how it works out for us. Again, you can see the AI just calculating all the states, scoring each state, and then choosing the best state for itself. This part is where the code is a bit slow, but we can work with it. Okay, so the AI has blocked us from playing horizontally, which is pretty smart. Now I can still try and capture this vertically, so let's just try that. Hopefully it blocks us from doing it. So let's see. Okay, so the AI has blocked us, and we can no longer capture that vertically because it's on top of us. Um, now let's just put it into the fourth column and then see where it takes us. Okay, now if we don't place the coin here, the AI will actually win, and we don't want that. So let's just block out the second column. Okay, so as you can see, there's actually it's actually quite competitive, and we can further enhance this by increasing the depth. But if we were to do that, it'll come at a cost of a time. So we're going to be wasting too much time looking at uh, so many states, and with a branching factor of 8, it's actually going to add up to a lot. So as I've been saying, in part 2 of this, we'll take a look at how to implement alpha beta pruning to cut down the search space, and then we can also take a look at parallelization and see if that actually helps us.